In this video, I'm going to demonstrate the HP WAN SDN controller working with Mininet. For more information about the HP WAN SDN controller, please have a look on the HP website. Under Products, you'll be able to download a 60-day trial of the HP WAN SDN controller software, as well as get details about this product. In this example, I'm running the HP WAN SDN controller within VMware on the required software, Ubuntu 12.04.2 LTS. The version of the HP WAN SDN controller used in this demonstration is 2.0. For details on how to install the operating system, the prerequisites, and the HP WAN SDN controller software, please have a look at my other videos, which you can find on YouTube and other places. Using Chrome, I'm going to connect to the IP address of the controller and port number 8443/SDN/UI, which is the user interface. By default, the controller uses a self-signed certificate, so you'll need to accept it to continue. I'm going to click on Proceed anyway. The default username is SDN, and the default password is Skyline. So logging in, I'll be able to see the default screen which displays alerts on the system. You can also view installed applications, and one of the applications here is the Link Manager service, which discovers the links on the network. We also have the Node Manager service, which discovers nodes or hosts connected to switches. These services are required for the HP WAN SDN controller to dynamically discover devices in the topology. Please refer to my other videos for the theory and background of these services. So clicking on the OpenFlow topology, at the moment no devices are connected. In PuTTY, I'm going to SSH to the controller, so 192.168.56.7, port 22. Log in with my username SDN and password Skyline. To make sure that everyone can see this clearly, I'm going to change the settings and set the font to 14. So hopefully everyone will be able to see clearly. So in Ubuntu, I'm going to type sudo mininet. I'm going to specify a topology of linear with 4 switches. That essentially creates 4 switches back to back. In this case, we're going to specify that the controller is remote, and we could specify an IP address of the controller, but in this case, the controller is running on the same machine as Mininet. Mininet has its own built-in controller, which we don't want to use. In this example, we want to use the HP WAN SDN controller, so we're telling Mininet that we're using a remote controller. Enter the password, which is Skyline, hit enter, and then hopefully on the controller, as you can see here, it has now discovered 4 switches. I could change the view to display ports, and I'll be able to see how these devices are connected to each other. Back in Mininet, I'm going to use the command ping all, which will allow the controller to discover the end devices. Mininet devices do not send traffic by default, so you have to initiate the sending of traffic by using the command ping all or another command to generate traffic on the devices. In the controller, I could change the label to display the IP addresses of the devices. I could also display the MAC addresses of the devices. So the controller automatically learnt the switches in the topology as soon as I started Mininet, discovered how the switches are connected to each other, and then discovered end devices. So going back to applications, the Link Manager service is used to discover the ports or the links between the switches. The Node Manager service discovers hosts or nodes. These are built-in services available in the HP WAN SDN controller. You don't have to configure them. They are available out of the box. So here's our topology. I'll now exit out of Mininet. And what you'll notice is the devices on the controller will disappear. So they go gray, and then after a short period of time, they disappear. When you exit Mininet, you are essentially unplugging the network. Mininet allows you to create a virtual network in a similar way to what you get using GNS3 or Simware. It is an entirely virtualized OpenFlow network. So when you exit Mininet, you are logically unplugging all the cables and turning the devices off. Hence, the controller displays that no network devices are available or connected at this time. So let's start the Mininet topology again and look at some of the options available in Mininet. Notice it's discovering the switches. And if I send pings, it will discover the hosts in the topology. Mininet switches are pure OpenFlow switches. Within Mininet, I can use the command nodes. That shows me the switches in the topology, the hosts or nodes, and the controller. Using the command net will allow me to see how devices are connected. So as an example, switch 1 is connected on its first Ethernet port to host 1 and second Ethernet port to switch 2 on Ethernet 2. So notice switch 1, port 1 is connected to host 1, port 2 is connected to host 2. Mininet doesn't have a GUI interface, but the HP WAN SDN controller allows you to view visually what's happening by creating a topology diagram. I can see the IP address of devices, so host 1 ifconfig. Notice host 1 has an IP address of 10.0.0.1. So within the HP WAN SDN controller, change the view to display IP addresses. Notice the IP address is 10.0.0.1. Notice the MAC address ends in 25. So node MAC address ending in 25. If the MAC addresses are too difficult to read, what you can do within Mininet is specify MAC to make the MAC addresses simple to read. So that'll start Mininet again. I'll do a ping all. Notice some pings may fail initially while the controller discovers where the devices are on the topology. So notice initial pings are failing while the controller is discovering where the devices are. At this point, it's still discovering node 4. There you go. It's just discovered node 4. And now, hopefully, when we do a ping, the pings will all succeed. In this case, we lost 1 ping. Let's try again. Notice 0 pings were lost. The controller now knows where all the devices are in the topology. So, host 1 ifconfig. Notice the MAC address, bunch of zeros and a 1. That's the first host. I could change the view to display the IP address once again, in this case 10.0.0.1. Mininet nodes are like mini Linux hosts, so you could, for instance, type host 1 ping host 2 and set up a continuous ping between the devices. You can also enable other options, such as setting up an HTTP server. So there's a basic topology of 4 switches. Let's create a more complicated topology. So I'm going to exit Mininet, and in this case, I'm going to change the topology to a tree with a depth of 3. This creates a tree with a fan out of 3, which is easier to explain with a picture. So notice the devices have been discovered. We've got a single switch, core switch, connected to one other switch with 2 switches connected to it, so a depth of 3. To discover the devices, we'd use the ping all command. Devices on the network are now being discovered. Pings may time out, so ping all I'll click on Clear ARP Cache so that the devices are rediscovered. The pings are failing because the controller needs to discover where all the devices are on the topology. But once the controller has discovered where the devices are, the pings will succeed once again. So this is normal behavior initially. You've got to remember that this is a brand new network that's just been plugged in, and the controller needs to discover where the devices are. So in this example, you can see that two PCs are connected to each leaf switch. Do the ping again. Notice no packets were lost. All devices were discovered in the topology. I'll change the view to show ports. Let's shut the link down between switch 5 and switch 7. This can be useful for testing. So link S5, S7 down. Just before I do that, notice the link is up. Notice the link has gone down. The devices are no longer connected. I'll bring the link up again. Notice the link has been discovered between the two switches. The two protocols that are used to discover links between switches are Link Layer Discovery Protocol, or LLDP, and Broadcast Domain Discovery Protocol, or BDDP. BDDP essentially is a broadcast version of LLDP. Going to OpenFlow Monitor, we'll be able to view the devices in the topology and the negotiated version of OpenFlow. So as an example, switch 2 over here has negotiated to use OpenFlow 1.0.0 with the OpenFlow controller. The HP VAN SDN controller supports OpenFlow 1.0 and 1.3 in version 2.0 of the controller. Later releases may support different versions of OpenFlow. Going to summary, we'll be able to see that this switch, data path ID, which is essentially an identifier for this device, has negotiated to use OpenFlow 1.0. So going back to the topology, this is a 64-bit identifier for a switch. The lower 48 bits is the MAC address of the switch. The most significant 16 bits is vendor dependent according to the OpenFlow standard. In this case, it's set to zeros. On an HP provision switch, that would be equal to the VLAN number. So VLAN 10 would have a number of A. So going to summary, once again, the data path ID, which is the identifier for the switch. You can see the IP address. This is running locally on the controller. This is the ephemeral or dynamic port number that the switch has negotiated to use when talking to the controller. The controller listens on the well-known OpenFlow port 6633. The negotiated version is 1.0.0. The number of tables that the switch supports is 255. The number of buffers is 256. And the capabilities of the switch include these. The ports on the switch are listed. So this switch has 3 Ethernet ports connected to the outside world. And I mean, this is all logical. I will show you in other videos how to connect a physical switch to the HP VAN SDN controller. But in this example with Mininet, notice this switch has 3 ports, 1, 2, and 3. According to Mininet, these are 10 gigabit interfaces, but be aware this is a virtualized environment, so that's not entirely true. This interface is the management interface of the switch. So if you were sending information to the management port rather than so-called physical ports in the switches, you would send it to this port. So what flows are available on the switch? Now flows time out after a period of time. So I'm going to generate some traffic by doing a ping all on the network, and hopefully what we should see is that flows appear. So by refreshing the page, I can now view the flows. So as an example, looking at traffic, a device with MAC address 1, so this is IP version 4 traffic, arriving on port 1 is sent out of port 3 if going to a device with MAC address ending in 8. So let's look at the topology. So I'll go back to MAC addresses. We're looking at switch 2, and we're looking at the port numbers. So in other words, MAC address 1 going to MAC address 8, traffic should arrive on port 1 and go out of port 3. And that's what we saw. So on switch 2, looking at the flows, notice source MAC address is 1, destination MAC address is 8, traffic coming in at port 1 will go out of port 3. So this is an OpenFlow table as displayed on the HP VAN SDN controller. We'll be able to see the number of packets and bytes that match this entry. So if I send some more traffic, we should see that information increment. Notice 1 going to 8 now displays 3 packets and 294 bytes. To see this on the physical switches, we could use the command dpctl within Mininet, and notice there are various arguments we need to supply, but this would allow us to, for instance, dump flows. So dpctl dump flows. I'll send some pings just to refresh the tables. Notice we'll be able to see the flow entries on the switches. So scrolling up, we should see an entry for switch 2. So there's switch 4, switch 3, and switch 2. Notice we have traffic with a source IP address of 10.0.0.1, destination 10.0.0.8. Notice the action is to send the traffic out of port 3. So not as easy to read as perhaps on the HP SDN controller, but what I'd like to point out is that the information is available on the flow table of the switch as well as on the controller. dpctl essentially allows you to connect to a switch and view the flows directly on that switch. So now let's only send traffic from host 1 to host 8, and I'll send a single ping. And now if we look at the flow table, we see less information, which is easier to read. Notice source IP address 10.0.0.1 going to 10.0.0.8. Notice source IP address 10.0.0.1 going to destination of 10.0.0.8. The ether type is IP version 4. Notice IPv4, and the action is to send it out of port 3. So the HP VAN SDN controller shows you visually and nicely what a OpenFlow topology looks like. I'll send pings between all the devices to refresh the flows. Notice I can view the IP addresses of devices. I can move devices around in the topology. I can also look at the shortest path between devices. So I'm going to set this as the source device, that as the destination device, and the controller will show me the optimum path or the shortest path between those two devices. Now it's not as clear in a topology as small as this. So let's run a script. So this is a Python script that creates a more complicated topology. So sudo bin ttpy and the IP address of the controller. Notice quite a few switches display in the topology with redundant links between the switches. I'll now send pings between all the devices. And the HP VAN SDN controller will now discover the devices in the topology. Notice this switch has 6 devices connected to it. The pings are once again timing out while the HP controller discovers where the devices are. And notice here, it's discovered the full topology. I'll do a ping again to ensure that the pings all succeed. Notice no pings have been lost. And there are the devices in the topology. So as an example, looking at host 10.0.0.1, making that the source, and host 100022, making that the destination. Notice the traffic in this example is flowing via switch 2. Now in another video, I'll show you a script that manipulates the traffic and sends the traffic through another switch. So firstly, I'll show you how to send traffic via switch 1, and then how to implement traffic engineering using a simple bash script or Python script to send traffic via other paths. The controller allows you to select follow flow, where you can look at specific traffic of specific devices and then view exactly where that traffic's going to go. I'll do a ping all just to refresh the tables. Notice HTTP traffic will flow through switch 2. If we look at the flow table of that switch, you'll be able to see detailed information of flows. These flows will time out and are dynamically updated. But notice there's detailed information of the flows within switches. So as an example, this switch, view details, will show me the flow table, which is dynamically updating with traffic in the network. So once again, looking at shortest path, notice the traffic is going through switch 2. But if we drop a link in the network, the traffic should dynamically reroute via switch 1. So link, switch 2, switch 14, down. Notice the link's gone down. It's a dotted gray line and should disappear. There you go. And notice the traffic has rerouted via switch 1. So that's at the moment the shortest path. If we bring up the link, notice the traffic is now rerouted via switch 2, whereas previously it was switch 1. So let's do that again. Bring the link down. Traffic hops to switch 1. Shortest path is via switch 1. Bring the link up again. Traffic now goes via switch 2. So the HP WAN SDN controller has a shortest path first algorithm built into it. In other videos, I'll show you how OpenFlow trace works, do Wireshark captures, and show you other options available in the HP WAN SDN controller. I hope you found this useful. All the best with your studies.